So the second tutorial lecture will be given by Professor Ben Arous from the NYU, and the title you cannot see, but I know is the complexity of random landscapes.
Thank you so much, Wayco. So I want first to thank the organizers for this invitation. As you've understood from my questions in the last talk, I don't know zip about biology. I don't even know what a ligand is, but still I found the last talk fascinating, of course, because it was the BBP transition all along. So then suddenly we understand. That's so here I was asked to talk about the results we have about complexity of spin glasses or random landscapes in general. So I chose to do that with a chalk because I had no idea who would be listening. Of course, it's a little ridiculous because, of course, I can see some people here who know a lot about that, but I will pretend that you know nothing. Okay, and so and I will try to cover both questions about statics and dynamics that I believe might be interesting to this interface with biology, and I'm sure are interesting given what I just heard. So let's start with a question. So I want to talk about random functions. Is that large enough for you read that? Okay. Or landscapes, if you want. Many variables.
Wait, are all random functions landscapes?
What?
Are all random functions landscapes?
What is a landscape? It's a function.
Okay.
It's just of many variable. All right, so for the moment, let's do that like math. I don't care what the function is for. Of course, you have examples, but let's just look at it from purely mathematical things. So you take a function, we want to understand a function, f, let's say, from a manifold M, and with real values. So this could be an energy, a fitness, an empirical score if you're doing machine learning. And this function, we will always assume it to be smooth here so that we can talk about complexity. And the important thing is that you want that the dimension of M is n, the number of variable, and this goes to infinity, right? So your n is very large. Okay, so that's the context. Now you want to understand, so, okay, examples of that. Of course, the first example we have in mind when talking about spin glasses, that F is the Hamiltonian. So I want it to be like that, and I want it to, of course, to be random on top of that. So it's the Hamiltonian of some disordered physics system. So of course, spin glasses come to mind. So, and then in this case, n is large, meaning you are in you have a large number of atoms, spins, whatever. Yeah.
Can I ask a question here? But that M would be a discrete space, right?
No, not discrete. And what I'm describing here, it's not discrete. Because otherwise, of course, it could be discrete. For instance, for spin glasses, it could be the vertices of the hypercube.
Right.
Yes, I won't do that. For a very simple reason. What is the topological complexity on a discrete space? Makes no sense.
But I can presumably smooth the spins and make it like a 5/4.
We could do that. Yes, we could do that, and then it becomes that. Or you could take the tap complexity. Let's forget that. But the important thing is that the vertices of a hypercube is not a CW complex. There is no Morse theory on it. Right? So let's stay for that because it's simple. So second, of course, the one that it could be the empirical loss of or a statistical problem in high dimension. right? So you have a statistical problem, a loss, you have a sample, and then the sample gives you the empirical loss. You have the true loss, which of course you don't have access to. And then you have the empirical loss, which is the function that you will then try to minimize, right? That's what statistics is about. And in high dimension, this is called machine learning. Okay, so there's a lot there. But and then there's the third one, of which you understand I know zip, but what we just heard, right? Fitness in biology. Fitness landscape in biology, where the N will be large. So these are the examples. What are the questions we want to talk about? Of course, I will be more specific and give you more detailed models, but these are the three classes of model you may have in mind. So, but the important thing now is not the model, but what are the questions? And asking questions. So the first thing is indeed to understand the complexity from a topological point of view. So that's problem one. So what is topological complexity? That your landscape looks like this, right? Which means you want to look at, typically you want to look at the level sets or sub-level sets. You take a number u, you look at this subset, the place where the function is less than u. You could take larger than, if it's a fitness, you probably want to look at the larger than something. And then this defines a subset of your manifold, and you want to understand the topology of that. The question is the topology shape, if you want, of the level sets or sub-level sets complex or simple? Okay, and so for that, the basis of that, of course, is one way to look at that is, we'll come back to that, is Moore theory in math, which goes back to the 20s. So Moore developed that theory precisely. He was interested in the topological complexity of these sets for Morse functions. I'll come back to what that means. And made a link. This makes a link to something different, which is to the number of critical points. Or for Morse function in general, and I will see that most functions we're looking at are Morse function. So what does that mean? I will look at pret k of, let's say, v. That will, for me, be the number of critical points, or whatever I call it, u here. This will be the number of critical points f below, with values below u, with an index k. So let me remind you what the index of a critical point is. It's just the number. If you take a critical point, where the gradient is 0, you look at the Hessian, and you look at the number of eigenvalues that are negative. That's the index. Right? So if you have a local minimum, the index is 0. If you have a local maximum, the index is n. Right? And in between, you have all the possibilities. Okay, so this is a very deep part of mathematics. I won't go back there, but very classical and simple now. But there's a link between this and that. A priori, there's a big difference between the two. Even if you take a manifold, you take U to be infinity, the topology of a manifold is related to the number of critical points of any Morse function. There are constraints on that we will see.
Are we supposed to know what a Morse function is, or doesn't it matter?
It's trivial. Let me say what it is. The function is Morse if it's smooth, and the critical points are never degenerate. The Hessian doesn't have the 0 eigenvalue. Generic.
Generic. Yeah.
So nothing fancy there. All right, so we'll try to talk about that. So how would you describe a function which is topologically complex. It's, of course, a function where, for instance, you have a very large number of critical points, right? That's what we will, which also would mean, if you know more about more theory, that the topology of the level sets can be complicated, right? So, of course, you can imagine that. This tells you the story, right? Here I have then you have the sublevel set is made here of different pieces. Things much, of course, this is a stupid example in dimension one. If you're in much higher dimension, things can be way more complicated than that, okay? So that's the topological complexity. Why should we care about that? So the next thing, of course, it's not the question of dynamics. So imagine some dynamical system which is geared to finding, let's say, the minimum of f, right? Simple things. You may think of other things. You may think of Langevin dynamics, random dynamics. We're talking about a Gibbs measure. I'll come back to that. But for the moment, think of the simplest thing, where I don't need to introduce anything if you don't know what that is. Think of a gradient descent for f, right? So let's say gradient flow for f, or gradient descent, which is the same thing in discrete time. And you start from a point at random because you have no info. And you ask the question, how much time to get to the bottom of the landscape? That is to find the minimum of f, right? And do you find the minimum of f? Maybe not, right? What is the probability to find the minimum? So that's the question. And how is that related to that? Of course, everybody has in mind that the topological complexity is something that prevents this to be reasonable and fast, right? If you start in the picture I just gave you, if you start at random in one of those wells, you cannot descend and the bottom is here, you cannot go there, right? Now, if you add noise to that, you will go there because you will end up getting out of this well and going there. But it may take a very long time, right? So that's the question that is here. And so it seems that the topological complexity is really important to understand the dynamics. Here, there's a huge mistake that is constantly made. Problem one here is not the worst. It's not the worst part of problem two. Everybody thinks in low dimension. Our brain is equipped to think in low dimension. So in low dimension, what's the problem to find the minimum of a landscape? It's, of course, that you can be blocked in a trap, in a well. In high dimension, that's not the question. Okay? That's not the only question. There is problem three, which, of course, is crucial, which is entropy, beating entropy, which is completely different. And so to understand dynamics, you need to understand problem 1 and 3 here. So let me explain this. Don't worry, I'll give examples very soon. Let me give the simplest example of all. Take the sphere in n dimension, right? and now take a subset of that, let's say, or take a function f. Okay, or before saying that, let me explain something simpler, the question of entropy. Let me take one point. Let's say, so here's the sphere. That's one axis, the axis x1. Here you have, in this direction, you have n minus 1 directions. And you take this thing, the North Pole. We call it n, like North Pole, right? And now you take a little cap around it, right? So I just take a very natural part of the sphere. I decided it's at the North Pole, it could be anywhere, okay? Now I start a point at random, and I do, let's say, Brownian motion, random exploration. How much time does it take to find this cap?
E to the n.
It's exponential. Okay? And here, there's no complicated landscape. There's no landscape. The landscape is completely flat. Right? I'm just moving at random, trying to find a point. This is extremely long, and the reason is simply because this picture we have of a sphere is not good. In fact, if you look at the equator here, with a certain width epsilon, this equator, the pole, let's put it differently, the two hemispheres here have an exponentially small mass. They are tiny. So the important thing is to see in high dimension, this is not the right picture of the sphere. I've drawn that a million times. The right picture of the sphere is like this. That's how you should think. It's hard to think like this, but it's how we should think. The sphere is like this. These two things are the two hemispheres, and all that is the equator. If you start at random, before you find this tiny thing, it takes forever, right? So this entropy problem, which I illustrate here in this stupidest example, is always there, right? So we'll have to deal with that. Now, what is the question about complexity? Imagine that on top of that, your landscape is complex topologically, right? So you have a gazillion holes everywhere, right? I cannot draw that, but you know, a million holes. If you start at random, and it takes exponentially long to get there, there's a big chance that you will find a hole before. And then you get stuck, right? So the two problems are adding on top of each other. But maybe you don't spend that much time here, because here, what I did here was, remember, the function was purely flat. Let's imagine now that I take a function which is, let's say, minimum or maximum, minimum here, right? So it means here that if I take now a search, it will be a gradient plus Brownian motion. I start from a point at random, and I would have a drift pushing to this or to this one, right? I would have a drift. Now the question is, will this drift be a good or a bad thing, right? If it's strong enough, maybe you could avoid all the traps and find the one you want. If it's not strong enough, you will probably wander around for a long time, and then you have a chance to fall in trap. Okay? So we'll come back to that. But the important thing is to have these three problems in mind: the entropy, the complexity, and then to see the two problems, entropy and complexity, and then how this applies to dynamics. Okay, this is completely abstract. Let me now get into some examples. All right. So the so let's take first purely random landscape, purely random functions. Okay, and I'm looking now at random functions, and I will take them even simpler. I take random Gaussian random functions. Isotropic field. So what does that mean? Let's say I'm on Rn. I want this to be random, Gaussian, let's say centered. But for the moment, I don't have a signal. The average is 0. And I just want to, then the only thing I have to describe this is to give the covariance. So let me assume that the covariance of this function is that's what I call isotropic, is invariant by rotation. So that's really like an example for mathematicians, right? Which means the covariance is a function of the distance. The covariance of this f of x and f of y is a function of the distance between x and y. That's what isotropic means. Okay, the simplest of all. I'm sure some people understand what I'm doing here. What is this class of function? It's all spin glasses. Right? So it's not that stupid. And that's an old theorem that goes to the 30s and 40s, which describe this possible phi, right? Because for mathematicians here, you want this to be a covariance, so you want this function to be of positive type. And this has been classified by Harmonic Analysis School of Vienna in the 30s. And the model is exactly what we call the spin glasses. Phi of D has to be of the form sum of AP d to the p. And the AP have to be non-negative. And if you recognize this, this is exactly the class of spin glasses. So let me describe these functions a little more. So that's one description. Another one is here. You could just write f.
In the limit of high dimensions, it has to have this.
I'm sorry?
In the limit of high dimensions, it has to have this form.
No. If you want this to be equal, in fact, there is a sharper description. If I let this phi depend on the dimension, the class is a little wider. But if you want this to be the same for all dimension, it's only that. It's not in the limit.
Full dimension.
It's any dimension. That's a basic geometric harmonic analysis problem. So that's the invention of spin glass in the 30s, right? Except, of course, the way you would, I mean, the usual p-spin you all know, I guess, is another way to describe this is this. I don't give the usual normalization, and these guys are AB. Okay, that's of course what is called a p-spin, and this corresponds to exactly this with one term, dp, and the general model would be some superposition of and this BP square is AP in my formalization over there. So that's called the general spin glass, a mixture of spin glasses. And of course, when P equal 2, this is usually called the Sherrington-Kirkpatrick model. And when P equal 3, it's the P-spin model. All right. So here I define it on Rn. You could look at it. So if you look at this F on the sigma n, which is just the hypercube, these are the usual spin glasses. And the two models that are usually studied are this or on the sphere of radius square root n to normalize it. Right, so that's the spherical spin glass. That's the usual Ising spin glass. Okay. So these are very interesting random functions. And you see from this description why they are that interesting, right? They are very generic. They're just, and then from there, you see also that the great contribution of Giorgio, of Parisi, which is to recognize that the order parameter is a distance between two replica, is not that unnatural, because you chose something which is isotropic. The only thing is the distance. Okay, so that's the this thing. And then, so let's look at this example of purely random Gaussian functions, which are simple and isotropic. And let's ask about their complexity. Topological complexity for the moment. Okay, so let's look just at the case of a fixed P, the pure P spin. In a pure P spin case, which means and on the sphere, or the spherical model, or this function, right? So now let's forget everything I said. What is this function? If you don't take the probabilistic point of view as a Gaussian, blah, 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 this is just a random homogeneous polynomial, right? That's it. You cannot do simpler than that, right? So even the simplest possible function, that's a random P homogeneous polynomial, right? So you take a, right? So that's what a spin glass is. It's either an isotropic Gaussian field, or it's here just a random homogeneous polynomial. That's it. With Gaussian, it's not only a random here, it's Gaussian, which helps in the many of the computations were made. Okay, so now this is a random function in the sphere, and you want to understand if it's complex or not, right? So the answer is theorem, it is complex. Exponentially complex. So this theorem covers a lot of work, and it's not very precise the way I stated. So let me say it this way: if you can, there is a formula you can.
P greater than 2?
What?
Is this P greater than 2?
Yes, of course. P equal. So yeah, good question. P equal 2. Normally, if you think of the Sherrington-Kirkpatrick model on the cube, P equal 2 is the worst. But on the sphere, if you take P equal 2, you're taking a quadratic polynomial. So then everybody knows how to compute the number of critical points. What is the number of critical points of a generic quadratic polynomial on the sphere? It's 2n, right? Because if it's a quadratic polynomial, you can diagonalize it. It becomes sum of lambda I ui square in a new coordinate system. And then if your function is sum of lambda I ui square, then the number of critical points is 2n for each thing, right? So, of course, it's not exponentially complex for P equal 2 or P equal 1, but it's exponentially complex as soon as P is larger than 3. Okay, so what does that mean? So so the first thing that has been, so there's first the so-called annealed complexity can be computed. Meaning you compute, let's say you take the log of the expectation of the number of critical points, let's say of index k before a level u, right? You take all the critical points, you take a level u, and then you try to compute that, okay? The asymptotics of that. And so here, this thing will be, in the right regime for u, will be strictly positive. It can be computed. There is an explicit formula for that. There is a variational formula for it that I will spare you for the moment. So This tells you that the expected number, take k equals 0 if you want, the number of local minima below a certain level u, you can take u to infinity if you want, whatever. The number of local minima, this is more detailed, but think of that, the number of local minima is exponentially large. The mean number, right? That's what it means. Then, so this is an old result, which is due to somebody sitting here in my collaboration with me and Yoshi Cherny. And then this is the anneal. But then what you want to understand is the quench complexity. Which is, you want to understand this. That's the real question, right? You want to know this is much, much harder than this in general. In this case, it just happened that they're all the same. So that's the theorem. It's due to Gerard and Subag. Right, this was due, as I said, to Caccioni and myself. These are already all results. So this
Is true for all case or just for?
So here, I didn't say what U is and K is. K here is fixed, and I let N go to infinity. You can also study the K when K diverges with N, right? And it's true for every K. Simply the function, the explicit formula is different. And the U here is taken in the range of the extremes, right? I didn't give the proper normalization, but U is in the range of the value of the absolute minimum, right? So what is the picture that emerges from this?
So this is all on the sphere, right?
This is on the sphere.
And
Yes.
what is true if I'm just from Rn to R?
No, on our end, on complete our end, the situation is obvious. So that's not hard. The hard part would be to look at the vertices of the
Think if I have a discrete.
of a cube, but there again, you don't know. It's not the right structure topologically to talk about critical points. To talk about critical point, to really talk about more theory, this is a big deficiency of the spin glass literature, models and whatever. To talk about a serious function, we shouldn't talk about the vertices of a cube, but the whole CW complex of that. Forget if you don't know what that means. What it means, it means the function should be defined not only on the vertices, but on the vertices, the edges, the sides, and all these substructures, right? That's for if we had defined the spin glass on this, right? If our configuration were not simply plus minus 1 to the n, the vertices of the cube, but all these possibilities, then we would have a proper topological theory, which has never been done.
Well, but for discrete models, you can look at the local minimums.
I'm sorry?
In discrete models in sigma n, you can look at local
Yes,
minimums,
yes.
and it's the same behavior, similar behavior in terms of number, exponential complexity of the number of local minimums.
I mean, the physics is the same, the math is different.
No, it just doesn't mean anything.
The math doesn't mean anything.
No, what is the index?
Why do I care about the index?
I mean, the
care about
degree,
physics.
right? I mean,
What?
It's just a degree, right? I mean, you have minima and you have sort of, I mean, you have the same.
You don't.
structure.
Okay, so
I mean, I will talk about that.
I'm not talking about minima here. I'm talking about critical points in general.
Yeah, but you can have, you can have a point which has, k bigger ones.
But I'm not sure it's the same. So
And minus
for it to
k
make sense topologically, so that you can relate it to the topology, you need this CW complex.
But it has been done, right? I mean, there is discrete Morse theory that has been applied to this kind of.
Discrete Morse theory is on CW complex, not on the vertices of the higher
Yes,
cube.
but so you extend it in some natural way, and
But how do you extend naturally the spin glass when you have it on the
I
vertices?
can describe a result.
I know. But what I'm saying is that this is a problem. You first have to do that before applying the Morse theory. That's why I'm staying with the empirical thing. So anyway, so the result that this equality here is proven using the fact that using a second moment method, right? So this uses a second moment method, which means that what Gerard did was to compute the expectation of the number of critical points squared. right? And then he proved that it's essentially expectation of the number of critical points, n squared, right? So he proved that the variance is not too big. And so then once you have a result about the mean, then you have a result about the thing itself. This is very specific. That was pretty complicated, but it's done in this case.
But if you take u equals 0
What?
and if you look at all the ones near 0 rather than the extreme,
Yes.
then is this true?
The number of critical points is also exponentially complex, but it's not given by the same thing.
Right, it's not the same thing anymore.
Yeah. So let me.
And Gerard, to be precise, Eliran did the total number and k equals 0.
Yes, you're right. Eliran did that. You're perfectly right. Eliran did that for u equal infinity, the total number, and k equals 0. That is the local minima. Okay, I'm giving too much here to Eliran, but anyway. So now the question is, so this function is exponentially complex, which is a little surprising, but it's like that. So now what I want to do in this talk is also introduce open questions. So here's an open question for the people here who want to work on something. How to compute quenched complexity for a random function, Gaussian or not, when it is not equal to an yield. Okay. That is totally open for us. When I say us, I mean mathematicians. It has been, so I don't have a theorem for that, but in the case which I know, you have an yield equal quench complexity in the situation of, for those who know spin glasses, of replica symmetry or one RSB, one replica symmetry breaking. But when you have K RSB or full RSB, this will not work. Okay? So we need a method like this to compute quench complexity. And so there's work on that. You can do. There's a work with Valentina here and Giulio, if I remember well. Oh God, yeah, which gives us this, but using the replica trick, using integers between 0 and 1 and this kind of thing. So not rigorous mathematically. Mathematically, I have no idea how to do that. Right? So,
But do you think the answer is correct?
Replica.
The answer that you get from the replicas is correct or not?
yeah, of course, sure. But we.
When is it not?
Not correct.
When
It's not correct for lots of things, but it's not.
So in this case, I think it is. But in general, of course, this is also has been done in the physics literature. So, but for us, let's just stay on the math side. Any method that can compute this thing mathematically for more serious model than the p-spin, the pure p-spin. For instance, you just take, here's the problem. You just take a mixture of two pure p-spins, Fp and Fq, and you mix them. Let's say that here I draw the line that goes from, this is the p-spin model, and this is the q-spin model, right? And p and q are two numbers larger than 3. I take a mixture of 3, let's say 3, and this one is 16. I choose 3 and 16 because these numbers exist in the physics literature. There are examples of people who have computed this, right? So when you are here, you know that you can compute the quench complexity when it's pure. When you're here, you can compute. And then in the middle, so in this region, you can too. There's work by Eliran, Zaitoun, and myself. Mathematically, that's okay. In the middle, you expect there is a region where it could be full RSB. And then the anneal complexity is not the quench complexity. So you don't need to do something very complicated. You take a mixture of two homogeneous polynomial, and already you don't know. Right? So this is a really open question. So let me explain how this question is addressed. So I'll be very as fast as I can. So how do you compute anneal complexity? Anneal complexity, to compute it, you use the Cat's-Rice formula. So the Cat's-Rice formula goes back to the 30s, 40s, and it gives you a formula about, well, this, let's say, which gives you the expected number, that's why it's anneal, let's say critical points of index K below level U, in terms of the, it's an explicit formula, but which is in terms of the distribution of the gradient, the Hessian of F, the point X, conditioned by the fact that the gradient is zero. Let's think of a minute about that. You take your F, it's a Gaussian function, you condition by the fact that the gradient is zero, and then you look at the distribution of the Hessian. Okay? That's not hard because we are in a Gaussian context. So I'm in a Gaussian context, everything is Gaussian, conditioning by the fact the gradient is zero is just a linear operation. So you can compute all that. But now, what is this? This is a matrix, n by n, right? This random object. It's a random matrix, a random Gaussian matrix, right? So this is the link with, this is where you have the link with random matrix theory. Okay, so Cat's-Rice gives you this link. You know things about random matrix theory, you apply, you get all these results. There's one more thing to say. The random matrices here, in this case, the distribution of the Hessian condition, but are of course trivial. Because spin glasses are trivial objects. They are Gaussian isotropic. So of course, the random matrix behind this would have isotropic properties. So this random matrix in this case is just a GOE, a Gaussian orthogonal ensemble, a Gaussian random matrix with a little shift. Okay, so you stay in the family of very simple random matrices and you can do this whole story. Okay, now the
But just if I understand, so that somehow, because it's an n squared matrix and you've got n conditions on it from the gradient,
yes.
why you end up being in pretty much similar to normal random matrices. Is that right?
Yeah, it's because, first it's because the distribution is completely rotation invariant.
Yeah.
And so that's why you end up having a GOE.
No, but if I make enough conditions on it, then I start changing. But you're not putting very many conditions.
No, I don't put many conditions. It's
Putting
just
n conditions on an n squared matrix.
so now the so here is that was open question 1. Now comes open question 2. How to compute complex? So here it was. Okay, I shouldn't have done that, but how to compute quench versus anneal. So what you have here, by the way, Cat's-Rice allows you to compute the mean. It also allows you to compute any power. And then you would have, instead of having one random matrix, you would have a lot of random matrices. Okay? Now, and so you can compute the second moment. That's what Eliran did, and then show that it's like the first square. Yeah?
So just one question about what you proved with Eliran and on the P plus Q, so that when you perturb from P equal 3 to 16.
Yeah, but it would be valid in more general cases, but we did it.
What do you prove? You prove something at the level of the landscape or at the level of the ground state?
At the level of the landscape and the ground state near the extremities. We prove that.
So if you take the P spin P equal 3 and you add the small 16,
yeah.
So this statement about annealed and quenched it's true.
Yes.
For an entire range of energies.
Yeah, for an entire range of perturbation, if you mean.
Okay.
Now, question 2, which is there. So. Sorry.
Why do we want quenched complexity at all?
Very good question. I come back to that. Please remind me in 5 minutes if I had an answer. Of course, we want quenched, but Let me explain that. All right.
We want most probable.
So the Cat's-Rice formula for non-Gaussian. Let me explain. Cat's-Rice, a priori, is proved by Cat's-Rice, by Arous and Weber in the literature. This is all proved for the Gaussian case. Now, if your field is non-Gaussian, it's not that hard. We did a proof with Arous and never published it. Under 17 different conditions of smoothness, whatever, nothing terrible, you can still prove Cat's-Rice. Okay, it's not published, but believe me, it's true. And I'm sure you can prove it yourself. The real question comes later. Imagine even that you can apply Cat's-Rice, which physicists do look. This. They don't even call it Cat's-Rice. The question is here. Again, this Cat's-Rice will transform the complexity problem. Okay, the topological complexity problem becomes a random matrix problem. Right? As we said, we have to understand the gradient conditioned by the fact that the point is critical. But how do you do conditioning when it's not Gaussian? Right? The reason why the random matrix problem here was not too hard, it's because it was Gaussian, so the conditioning was simple. So here, this random matrix problem in general cases can be quite serious. Okay, so let me put.
But for the standard universality methods like Lindenberg's argument, can't you replace it by Gaussian?
I don't know how to do that. Okay. By the way, remember that universality for random matrices took much longer than Lindenberg. Right? So these are serious questions because, in fact, you have what I didn't say here. What comes here into play is the absolute value of the determinant of this thing, and so this is what you have to control here. And in general, it's not easy. Okay, so that's a question that is still open. But I still believe that this tool should be able to give exponential complexity of many non-Gaussian things. All right, so that's about the topological complexity. Now, let me explain. Yeah, in fact, just for the fun of it, I just give you the following result. If you take a random polynomial of homogeneous of degree p, the simplest thing, then this topological complexity is positive, exponentially large. Somebody, I forgot the name, Kozhashov in 2018, computed the worst case, right? The most complex possible homogeneous polynomial of degree p, and this complexity is just twice the one of the random one, right? So when you pick at random, you pick almost as bad as the worst you can ever do. I have no clue how to do the worst case, but the random case is what spin glasses are about. Okay, so now let me explain. So that was the static. So this tells you a random function, this is a very simple class, can be very complex. What about, oh, maybe I should go there, sorry. What about, I'm speaking, I'm sorry.
Mimi.
Yeah.
Is there something new which is expecting, which one expects from the non-Gaussian case compared to the Gaussian case?
I really don't know.
Heuristically, I mean.
I do expect it to be exponentially complex too, but the region, or there are many details that I'm hiding here that may be different. That I really don't know. Now, okay, so let's try to complicate this story a little bit, because what I described up to now was a purely. Now let's add a signal, right? So what I described was a purely random function, right? Purely random landscape. Let's add a signal, right? If you're doing statistics, machine learning, of course there's a signal. And now I don't know about biology, but I guess there's a small dimensional signal. That's what we've just seen, right? So let's add a signal. Let's take the simplest possible example of that. You take this random polynomial, right? I'm on the sphere. I take a new f, which is a random polynomial, and I add the simple possible signal. Right, I take one coordinate. So again, that my sphere, which as I told you is not a right picture of the sphere in high dimension. This is x1, and I just take this function, and k being whatever. Okay, so this is my function. So clearly, you expect, at least when lambda is large, that maybe the global minimum will be, or maximum, whatever will be, not at the equator, but close to the North Pole or South Pole. Right? This, when lambda is large, this is the minimum of the maximum of this function is just North and South Pole, and you add random noise. There is no reason that this, so what happens there? The important thing is that there is, again, I don't give you all the normalization, everything depends on n, but let's forget that. There is a critical value below which it's as if you had no signal. So the picture here is the following. All your critical points are at the equator. You have exponentially many here. That's the picture I drew before. You should look at it like this. You have your two hemispheres, and then you have a crazy landscape here with a lot of at the equator. And the global minimum is here and not related to the North Pole. Right? So this means there are no critical points away from the equator. The equator here is the region without any information, which means you've completely lost the signal. Right? How can that be possible? So that's, and then there is, of course, a region where you recover the signal. What does that mean? That means that you have a gazillion local minima, critical points here, but then at some point you find one in a parallel like this, which is the North Pole, right? And so, and then the more lambda is large, the more this thing goes up, and the more you recover the signal. Okay? So this is related to what we just heard in the talk before, even if you don't see it. So how do you see that? Why is that true? And of course, when lambda is large enough, you recover perfectly. Perfect recovery. So when lambda is not large enough, you recover your local minimum, whatever, global minimum is correlated with this, but not there. Right? And when lambda is large enough, all the scales are understood, it's very close.
Even for k equals 1?
No, of course, this is. So there is it's true for all of them. No, this transition is for k larger or equal to 2. Right? Of course, for k equal 1, things are instantaneous. I will come back to what happens when k equal 1, 2, and 3. So what is the, So what is the story here? The story is you apply Katz's Rice. Again, so you have to look at the Hessian of this thing, of f, conditioned by criticality. So that's, remember, the link with my random matrix problem. And what you find is that now it will be, as before, a GOE, a random matrix, the one you had when you had no noise, plus a rank 1 perturbation. Naturally. Right? Yeah.
So should I think of that as being 3 regimes, one where I don't recover anything, one where I recover partially, and one where I recover fully, or is that the partial and fully one are sort of connected? There's not a transition between.
There's not a transition between. It's just when lambda goes into infinity. That's 2 regimes in some sense. But now it doesn't block. It just goes up and up and up and up and comes close. And you can measure that quantitatively. I want to spare you all. So you see that it's a rank 1 perturbation. Look at the Hessian of this thing. But it's the Hessian of that plus the Hessian of that, which will be the second derivative of x1 to the k, everybody can compute, right? So you will have a rank 1 perturbation of a random matrix. which is what we just heard during the other talk. So this for me goes back to, this is called the spectral transition, called the BBP transition, which goes back to 2004 or 5, I don't know. And so let me explain that briefly. When you have a random matrix, so in this case, it's the spectrum of that is not the Wishart matrix. The spectrum of a GOE, we all know, is a semicircle, asymptotically. And then you have the same thing. At some point, you see an outlier somewhere there. So when you have the BBP transition tells you for this Wigner case or for the Wishart case, when you have a rank 1 or a finite rank perturbation of a random matrix, there are different things happening. So that's the thing to remember. And so one thing is there is a regime. So abstractly for the BBP transition, there is a regime where, so let me explain here for just rank 1, which is simpler. When you have rank 17, it becomes more complex. So there is a regime where lambda is smaller than a certain lambda c, and then the bulk, that's the most important thing. That's why that's the less obvious thing. The bulk eats the outlier, the signal. There is no outlier. Which means you have a signal, right? Take a Wigner matrix plus a rank 1 perturbation. You have a signal, and it is completely eaten by the semicircle. You cannot find it. Even, you can prove that even information theoretically, you cannot find it. So it's not simply because your statistical method is dumb. There's no way to get it. Right? So the signal is forgotten. Then there's another place where, that's what I was explaining, where the signal emerges as an outlier. As we've seen, and importantly, the eigenvector of this is not exactly the signal. The eigenvector here aligns better than random with the signal. Which means what? Which means here, the eigenvector corresponding to this outlier aligns with, since in my model it was E1, this vertical vector. It's better than random. What does that mean? If you take in high dimension, if you take a vector at two vectors at random, they are orthogonal. So if you take at random vector, it would be at the equator. Here, when you're above the transition, it begins to align. And then when you increase lambda, it aligns better. This is what we've seen. In all the examples we had here, the whole talk before was music to my ears because I saw BBP all the time, even though I understood zip. You see, of course, the difference in a real problem that you cannot simply turn up the lambda. This would ask for a larger sample size, which you don't have. But so you have a positive alignment, but which is not yet perfect, right? So this BBP transition is behind the story here of the topological complexity. So here, yes?
So can you prove that the eigenvector is the best estimate of the signal, or is that not true?
No, I cannot prove that.
Then you bootstrap to get it to the full.
Yeah, so come up with another one. We would love it, right? That's in particular in this region. The whole story. So to come back, I'm sorry, becomes a little more a discussion between the whole story we had in this paper. We understand also what happens here, right? So for instance, here's when you have no outlier, the top eigenvalue here fluctuates like in a different scale, and it's a Tracy-Widom distribution. When it's here, when it's alone, it's purely Gaussian, much larger fluctuations and Gaussian. When it's here, the eigenvalue fluctuates in a kind of intermediate regime that we can understand. And you can see that the eigenvector begins to correlate, but microscopically. It's just a little better than it should be in a purely random case. So all that is understood in these simple cases. All right, so that's this. So this looks like a completely formal example, the story. But the story is, in fact, the beginning of what is called tensor PCA, which I will not spend too much time on. So that's the first problem of statistics in which you can see that. So it's not the problem of biology here, it's problem of statistics. Here's the problem tensor PCA. I give you an unknown vector, u, in high dimension, let's say unit vector, and which is unknown. And the only thing you have access to are u plus noise. And w is a tensor, so that's, I'm sorry, u to the p. Okay. So you have a tensor, it could be 2 if you want, right, which is rank 1. Here, in this very simple example, and you don't have access to it, you have access to a noisy version of it, as always in statistics. And you have a sample of that. With this data, can you recover u? Right? When p equal 1, this is linear regression, right? We all learned that in Statistic 101. P equal 2 is a critical case, p equal 3 is interesting. So how is that related to the story I'm telling you here? Take this statistics problem, do the simplest thing that you learn in statistics, which is maximum likelihood, Gaussian case, so simple. You compute the log likelihood, and what do you find? This function. Okay? So when you try then to do maximum likelihood, maximize the likelihood, you're exactly the kind of problem we have here. Okay? So this is with for rank 1 tensor PCA. You could imagine now that your signal is rank 17, and then the story becomes way more complicated. All right? Yes?
How much is known about when the features are correlated, when it's not isotropic anymore? Are there results, very many?
If it's Gaussian, it can be done. If it's not, and not correlated, then good open question number 4. So here, let's stay on this for a minute. So you do maximum likelihood estimation for this. Okay? Easy to do. Then you compute the likelihood is this, as I said, the log likelihood, or a variant of that. So now what I'm telling you is that the likelihood, the landscape of the likelihood is complex, right? You have exponentially many local minima, your algorithm could fail. But now there's also the question of the dynamics, which I didn't talk. The landscape is complicated, but is it important or not? So let's talk about dynamics. So we could talk about dynamics in a random landscape, in high dimension. Or, different point of view. So you have your random landscape F, and then let's say you take either the Langevin dynamics, we all know what that means, that is you take, or the gradient flow, or this. Oh, wait a minute. I'm not allowed to do that. First, I have to answer your question. So before I go to dynamics, let's stay with statics for a minute. Positive temperature. That's your question. So for the moment, I treated the following question. I have a random function, and I want to describe that topologically it may be complex. Now let's imagine a minute that we're doing physics, and so we're looking at the Gibbs measure. Right? That's what we Gibbs measure at inverse temperature beta. That's, of course, what you do for, let's say, well, this is a reference measure on the manifold. So that's what you do for spin glasses, right? So what I described was a completely zero temperature thing, the shape of F. But that's not what you want to do in physics in general. What you want to understand here is the structure of the Gibbs measure and the structure of the free energies. So this is, of course, so this is, as you know, a very long story. Parisi, Talleyrand, many more. And then, so let me explain quickly what has been done using what I just described. The usual physics approach, the Parisi approach, goes from very hot temperature down to zero. When beta is very small, this thing is like the uniform measure, right? That's a high temperature regime for it. And then the hard part is to go down and get into what is called replica symmetry breaking. So we understand, so there is this Parisi formula, proved rigorously, you know, as we said, we heard there are 2 Nobel Prizes for that, which gives you a formula for the free energy, right? So the free energy is, which is of course simply computing that. So this free energy formula, which is given by a variational problem, has been given by Parisi a long, long time ago, proven by Talleyrand mathematically. And then you have the this description of this story. And from that, you understand the Gibbs measure structure. Now, what we could do here, and the hard part is to go down in temperature. Has been done, in fact. Once you understand the quench complexity, you can try to do that in reverse. Start from zero temperature and try to raise the temperature to understand the structure of the Gibbs measure. And this has been done. So let me explain that before I go to, how much time do I have?
5.
What? 5? 5 more? All right. So, okay, dynamics will be short time. So the structure, of course, you see in temperature that, so you have, you know, you compute the global minimum, it will be at a certain altitude, this is the energy. And so you will have here the global minimum, and above it you will have very large, you will have a lot of other local minima. What you can prove in the case of the p-spin model is that around each of these you have indeed wells, and that the Gibbs measure at a positive temperature will concentrate by the equivalence of ensembles at a certain energy, and will be concentrated on those rings, right? You have the wells, and so if you look at the sphere, which of course shouldn't be looked at like this, your Gibbs measure will be concentrated on random wells, right? Only not an exponential number of them, right? For each different temperature. So there's a whole story about whether these wells change with the temperature. This is called chaos in temperature. Well, that is understood. But then what happens, so this has been done for the p-spin model. If we could understand complexity for a more complicated thing, we could also do that. So this answers your question, in fact. And then there is a certain temperature, energy, whatever. When you come at this level, suddenly the Gibbs measure is no longer concentrated on that. So when you are in this structure, this explains much better the 1 RSB phase, if you understand what that means. If you take 2 points at random under the Gibbs measure, only 2 things can happen. They are either in the same well or in 2 different wells. And this explains that their overlap, their distance, if you want, has 2 possible values. Right? That's the 1 RSB of Parisi. Now, there's a temperature. Well, I could do that with temperature. There's a temperature here, T stats, and at this thing, you have the transition between what is called 1 RSB to replica symmetry, right? So things seem simple. What this topological picture brings is much more than this description. In fact, it shows that there are 2 other temperatures here in the supposedly trivial phase. So there's one which in physics is called TD, like dynamical, that we call T shattering. In this region here, The Gibbs measure is now carried. It's not like the uniform measure. It's not carried by a finite number of things. It's carried by an exponentially large number of wells. Okay, that's the shattered phase. Your Gibbs measure. So when you take, and you cannot see that. This shows that the overlap is not the right variable. Right? What we learn in spin glasses is the distribution of the overlap explains everything. No, not at all. And of course, that's known in physics. But so the overlap here, when you take 2 points, if you have an exponentially large number of them, there is a very large probability that they will never fall in the same. So the overlap is always 0. But the structure is very different than uniform. And this is why, in fact, this TD is also the dynamical transition. Below this, the dynamics are slow. Even though here, even though the equilibrium measure is, it's replica symmetric. Yeah?
Is there any feature in the partition function at that temperature?
Is there any what?
Feature in the partition function, in any derivative of the partition function?
No. It's just the structure that I'm giving. So this is exactly like in the random energy model that Veronique knows well. In the random energy model, you have the same thing, a very low temperature phase, where the Gibbs measure is concentrated of finite number, and then exponentially. And then above that, above this, the dynamics is fast when you start from a point at random. But there is still another temperature, which we called in our paper with Okosh-Jagannath, the BBM transition, the Bara-Burioni-Mézard transition, which means above this, the dynamics are fast, even if you have somebody against you choosing the starting point. So, whereas here, they are fast if you start, here they are fast, and here you can have slow dynamics here if you start from a bad point. Okay, so that's the story. Anyway, so that's the picture we have here. What? Okay, I'm too short. I'm short on time. What now if you have a signal, as I explained? Because that's the important thing. Now, if you have, so I take 2 more minutes. If you have a signal that I explained in the statistics model, you don't want to be in a regime where your dynamics are exponentially long. An algorithm that takes exponentially long is not good. So you want a dynamical transition. You want to make sure that the dynamics, which will be gradient descent, let's say stochastic gradient descent, are fast. This happens for when you have a signal. There is a whole regime where the dynamics are not fast, even though your signal is above all these thresholds, even if the signal diverges like a certain power of n to the p minus 2/2. So why that? The dynamics do not work in short time. So why that? It's because of the other. So again, that's the picture. You want to get here. You start at random, so you start at the equator. You have a drift pulling you up there, right? But again, that's what I told you before. If the drift is not strong enough, then you stay for too long. At some point, you escape, but you stay for too long at the equator. And if you stay for too long at the equator, then you meet your death. You meet a hole, and then your algorithm is very long, right? So this transition is really a serious thing. And so, to be brief now, and to link with the former thing, what we've been doing after that with Reza, who was here, and Okosh, and then with Okosh, Reza, and Zhao Yang, is the following story. This example I gave you of tensor PCA is one particular example that links the story of statistics with the story of spin glasses. But then we could look at whatever other problem of statistics in high dimension. And we started from, and so we first did it for rank 1 things, and then for a much more general thing. And the story was the following. We started from the Occam's razor. That is, a problem in statistics will never, even if you have 10 to the 9 parameters because of your neural net, it will never work in 10 to the 9 dimension, really. It will always be in a low dimensional structure, like we've seen. There, the dynamics are not, sorry to point at you, there the dynamics are not given by an algorithm, but by nature, evolution. But it's an evolution which seems to be happening in low dimension. Not dimension 10 to the 9, but dimension, I don't know, 17. So we started from this principle because that's what happened in every one of the examples we had. And what we did for that is to give first a Bourbaki approach, which means a completely abstract set of conditions that guarantees that something happened in low dimension. Of course, in many of the statistics problem, we could guess what the low dimensions were. Whereas in this problem, you can't really. Or maybe you can guess, but you're not sure to get everything. And then, so that's the first thing we did. And we had all sorts of machine learning algorithm that we showed worked, in fact, in low dimension. So what does that mean? You have dynamics in dimension 1 billion. I'm saying that there is a projection in dimension 17, which is autonomous. Right? That's not natural. If you have an ordinary differential equation and you project it, it will not be autonomous. But we give conditions for that to happen. All the action is happening in this foliation. Now, the real question, of course, is how do you find this projection when you are in dimension 10 to the 9? How do you find the 17-dimensional projection if you don't know it? One way, that's what we then did with Zhao Yang and Okosh and Reza, is spectral, is to use the BBP transition. So how do you use the BBP transition? You have this thing with a signal, which you assume something is happening in low dimension. You have two ways. One way is you take your function and you take its Hessian at a random point. Then it should show a BBP transition, right? So if your function is essentially a function of 17 variables, in 17 direction, it will be very curved. In the other direction, it will be very flat. So when you look at the Hessian, the eigenvalues corresponding to this direction will be much bigger. So you should see that as the outliers of the Hessian spectrum. That's one way. And this would be on the Wigner thing, because you would have typically a semicircle type of thing. You don't care what the bulk is. What you care are the outliers. Another way is to look at the Gram matrix. Imagine now that you have a stochastic evolution, your dynamics along the time. Then you could take the gradient at every point. This gives you a rectangular matrix, and you take the singular values of that. And then you are in the Wishart word, XX star, the one you have. And in this case, again, the outliers, if the signal is strong enough, come out. And the important thing that we saw was a dynamical BBP transition. When you start at random, you have nothing in the spectrum. As soon as your system begins to evolve, trying to find then you see gradually the outliers coming out, right? And this is complicated. That's why one should be prudent. It could be that you have outliers coming out, but less than the real signal. You have a signal of size 18 and you see you could have outliers coming out and coming back in the bulk. That's not, or outliers coming out and they are not good enough. They are not really correlated to do anything. So when the signal is strong enough, or when you wait long enough in the evolution, all that becomes clear. But the murky region in between can be really murky, right? So in real cases like this, you cannot simply increase the number of sample. So it's hard to tell whether this murky zone, that's what you were describing, carries a signal or not. Okay? And because of what I said on the BBP transition, it's quite possible that you have a lot of signal that has been definitely eaten by the noise, and you have no way to recover it. Okay? So that's, I don't have time to explain this last bit, but that's how it relates to this story.
One quick question.
Just behind you. Oh.
I don't know if I understand it correctly or not. You told us that in T-dynamic, overlap or the distribution of overlap is not enough to understand the behavior of the system.
Yes.
So any other order parameter to understand? You mean it's not enough, or we should add something else?
Depends what you want to describe. But it's, yeah, there is more than the order parameter, than the overlap distribution.
For example, for a single system.
Yeah.
We are just looking at overlap to see if it goes to phase or if it can represent different phases of the system.
What I'm saying is that in this region, if you take 2 points at random under the Gibbs measure, like Parisi tells you to do, the overlap will be 0.
Oh.
Exactly like for the uniform measure, where the structure is shattered. It's well known. I'm not inventing this, George. Everybody knows that, but it's shattered. Like in the REM, you go back to the REM, the random energy model, and then that's exactly what happens. You have this region where you cannot detect it on the.
The overlap could not be an indicator of the behavior of the system.
No, here the overlap distribution is trivial, but still the system is not trivial at all. And in particular, that's what explains the difference between the static and dynamical transition.
Thank you.
All right, so maybe we should thank Professor Bernard for a nice talk.